You know, we hear the buzzword the cloud tossed around literally all the time, creating this illusion of a magical, invisible force floating somewhere above us. But today, we're going to look right past that. We are going to break down the physical, tangible reality of the internet layer and see exactly how our digital world is actually stitched together.
Seriously, think about it for a second. You open your browser, you connect to your Wi-Fi, and your data goes to your local internet service provider. But what happens next? How does your tiny data packet actually navigate the absolute chaos of tens of thousands of independent, global networks to reach its final destination, like a Google server or a Netflix database, in just a matter of milliseconds?
To figure that out, here is our roadmap for this explainer. We're going to hit 5 key areas, starting with AS and ISPs, moving into the BGP routing system, checking out tier and IX architecture, tracking a packet's global journey, and wrapping up with the destination and next stop. Let's get right into it.
Section 1. What exactly are AS and ISPs? Let's lay down the foundation here.
Okay, so first things first. The internet is absolutely not one giant network run by a single all-powerful company. Not even close. Actually, it's way better to think of it as a massive global highway system. The sole job of this internet layer is just routing data across the world, taking a packet of information and ensuring it travels down the right paths to reach literally any system on Earth.
Now, to build a highway that big, you need separate roads managed by totally different entities. So instead of one cohesive web, the internet is actually made up of tens of thousands of individual networks. We call these autonomous systems, or ASs for short. And the key word there is autonomous. Each one is completely self-managed. It has its own routers, its own routing policies, and its own specific block of IP addresses. The internet is really just these thousands of autonomous systems constantly interacting and connecting with one another.
So what does that look like in the real world? Well, every major player gets an AS number. Your local ISP, say Changhua Telecom, operates as AS3462. And they are constantly connecting to the massive networks of tech giants like Amazon, Google, Microsoft, Cloudflare. You get the idea. The entire global internet is just one AS connecting to another AS, passing your data down the line.
Moving on to Section 2, the BGP routing navigation system. With tens of thousands of these ASs out there, how in the world do they actually find each other? Well, if we're sticking with our highway analogy, BGP, which stands for Border Gateway Protocol, is basically the internet's GPS. It's the vital system that tells your data packet exactly where the next exit is. Without BGP, a router wouldn't have a single clue whether Google is to the left or Amazon is to the right. And how that GPS gets its map is actually pretty wild. See, the internet doesn't proactively search for an IP address. It's the exact opposite. Companies actively advertise where they are. Google's BGP routers will literally shout out to the world, "Hey, I own the IP prefix 142.250.0.0/15. Cloudflare does the exact same thing for theirs. Then, ISPs all over the globe receive these broadcasts and use them to build these massive, super complex routing tables. So when your packet arrives, the router just checks the table for the next hop. All right, Section 3, Tier and IX architecture. We know how data navigates, but how are these physical roads built? And, maybe more importantly, who is paying for them?
As it turns out, not all ISPs are created equal. There is a pretty strict hierarchy here. They're roughly divided into 3 tiers. Down at the bottom, you've got Tier 3. These are your local community or campus providers, right closest to you. One step up is Tier 2, the bigger regional telecom companies. And then, at the very top, you have Tier 1. These are massive global networks like Lumen or NTT. They are so incredibly huge that they don't even buy internet access from anyone else. They just connect directly to each other to blanket the globe.
But here's the catch, right? Pulling dedicated physical fiber cables between every single ISP on Earth would be mind-bogglingly expensive. So the industry came up with a genius workaround, the Internet Exchange, or IX. Picture an IX as a giant physical intersection where a bunch of different networks, like ISP-A, ISP-B, and maybe Google, all plug their equipment into the exact same massive switch. It lets them swap hundreds of terabits of data per second directly, which slashes costs and massively reduces latency. Because of this setup, we get 2 core economic models driving our internet highway. Smaller Tier 3 or Tier 2 ISPs typically have to use what's called transit. Basically, they're literally paying a larger Tier 1 provider for a ticket to access the rest of the world. But at an IX, networks can do something called peering. Peering is when 2 networks look at each other and say, hey, let's just mutually exchange traffic for free. They hand the data over directly, totally bypassing those expensive transit toll booths.
Which brings us to Section 4, the packet's global journey. Let's tie all of this together and track a packet when you do something super simple, like clicking on a YouTube video.
So, you click play, your data packet physically hops from your laptop over to your home router and then hits your local ISP. From there, it gets sent to the ISP's core router, which, if you're lucky, is plugged right into a local internet exchange. At that IX, your packet is handed off directly via one of those free peering connections we just talked about, straight into Google's autonomous system, landing at a Google Edge server to fetch your video.
But wait, what if there isn't a direct peering connection nearby? Well, in that case, your packet goes on an absolute world tour. It might travel from Taiwan, dive deep under the ocean to Japan, cross the Pacific to the USA, hop over to Europe, and zip back to Singapore. This is all happening through massive submarine fiber optic cables managed by those Tier 1 backbone providers. We're talking literal cables resting on the ocean floor. Some of them even have to be armored against shark bites. No joke. And at every single stop across thousands of miles, BGP routing tables are instantly queried to find the next hop. Somehow, it gets your packet across the globe in just tens of milliseconds.
Finally, Section 5, destination and next stop. What actually happens when the packet hits the end of this insanely fast global highway? Well, the end of the line for the internet layer is almost always a massive, sprawling data center run by one of the big heavyweights, Google, AWS, Azure, OpenAI. Tracing this journey really proves that the internet isn't some magical, ethereal cloud floating in the sky. It is a highly structured, intensely physical network of submarine cables, heavy-duty routers, and autonomous systems. But here's the thing. The journey isn't actually over yet. Once your packet physically arrives at the destination AS, it still has to navigate a ridiculously complex internal maze. It hits an edge router, passes through firewalls, gets sorted by load balancers, runs through proxies and API gateways, all just to finally reach the specific server pod holding the exact data you asked for. And that leaves us with a pretty massive question for our next explainer. Once the packet leaves that global internet backbone, how do modern content delivery networks and anticast technologies actually navigate that crazy internal maze? How do they guarantee that you get a lightning-fast, low-latency experience no matter where you're standing on Earth? We're going to trace that exact path next time. So thanks for hanging out and exploring the physical internet with me today. See you in the next one.